Deriving the equation for elastic potential energy. This is for an ideal spring. So for this derivation, imagine an ideal spring being stretched from its rest position where there is zero stretch and zero force, and then as force is applied it stretches, and at some point it has stretch x with some force being applied. But going from zero stretch to stretch x, the average force would be F divided by 2. This can be seen on the force versus stretch graph for an ideal spring. Stretching from zero force, zero stretch, up to stretch x at force F, it's easy to see that the average force for this stretch would be halfway between 0 and F, which is F over 2. This force versus stretch graph for an ideal spring is a straight line, so we're thinking y equals mx plus b. But here we don't have y, we have F. Our slope is k, the spring constant. The x in your algebra book is x for stretch here. And there is no y-intercept, it is 0. So for an ideal spring, this is the equation that relates the force on the spring to the stretch of the spring. And rearranging this gives us really the definition of the spring constant, which is the ratio of the force to the stretch, or the amount of force needed for a certain amount of stretch, otherwise known as the spring constant. And additionally, we'll need to note here that the average force applied to stretch the spring is equal to the force at the full stretch of x, that's F right here, divided by 2. And right there, that is the average force right at that level to stretch the spring from a zero stretch to some stretch x. So now with the idea of work, we will derive an expression for the elastic potential energy in an ideal spring when stretched some amount. Now, there is no single force applied to stretch the spring. It steadily increases as the spring is stretched, but there is the average force that's applied, and that's the force we'll substitute here. There we go. And the distance that it's stretched is going to be x, giving us this expression. The work done to stretch the ideal spring is equal to the average force to stretch the spring times the amount of stretch. Remember that the average force equals the force at the stretch x divided by 2, so we can substitute, leaving this expression, which can be written this way. Now remember, we have an expression for F from the straight line of this force versus stretch graph. The equation of the line on this force versus stretch graph is the force equals the spring constant K times X, and we'll substitute Kx in there for F. Leaves us with this expression, which can be simplified to work equals 1/2 Kx squared. The work to stretch an ideal spring is equal to 1/2 the product of the spring constant of the spring times the stretch squared. Now, since the work done to stretch the spring is going to be equal to the amount of energy transferred into the spring, that would be the elastic potential energy. Which leaves us with this final expression for elastic potential energy. Elastic potential energy is equal to 1/2 the product of the spring constant times the stretch of the spring squared. And this is for an ideal spring only. Remember, that's was the situation here. And it tells us how energy in the spring is related to the stretch of the spring.